actually told me how to properly introduce invited speakers. So today this feels a bit like an exam to me now. So how should I introduce someone like Jan? I guess I could do that by referring to his scientific family. Jan was a supervisor of Bart Goethals, who all data miners among you surely know. He was supervised by Jan Paradans, who all database people surely know. Made important contributions to database theory and completeness results for relational algebra, for instance. So in a sense, I see this a bit like a sandwich of excellence in which Jan is in the middle. But of course, I could also refer to his own work. Jan has been quite active in databases. You could say he's a database person. But you might just as well say he's a theoretical computer science person. And actually, I don't really need any external confirmation for that. Years ago, when I did my PhD, I wrote a machine learning program that produces results in some kind of logical language. And about 10 years later, Jan actually characterized that language as a particular fragment of logic. So 10 years after I did the work, I finally had the idea that I knew what I was doing. Thanks to Jan. So theoretical computer science, databases, he's made many contributions in many areas, actually also on query languages. And recently his interest seems to have shifted towards natural computing, and more specifically DNA computing. And so that is what he will be talking about. It's about DNAQL, which is a query language based on DNA computing. So Jan, thank you for being willing to speak here, and the microphone is yours.
Thank you, Hendrik, for the very kind introduction. I really have no recollection of ever teaching you how to introduce an invited speaker, but you passed your exam brilliantly. I want to thank the program committee for inviting me. It's a real honor. And today I would like to talk about some work I've been doing over the past few years to understand the principles, let's say the theoretical basis of what is possible with DNA computing if you are interested in database applications. This was our quest, and I want to present this work to you. So before we really start, I want to give a brief introduction to DNA. For the purpose of computer science, it is quite simple actually. Of course, if you want to understand it really chemically, it is very complicated, but for computer scientists it is very easy. So the basic concept is that of a single-stranded DNA molecule, and this is a very long molecule that is composed of bases. It is a polymer of different bases, and so you can just think of it as a string, as a sequence of letters, where the letters come from the four-letter alphabet A, C, G, and T. And so this string is called a strand, and the positions of the string are called the bases. And so here is a small illustration. Please ignore for the moment the right-hand side and just look at the left side. And then there you see actually a DNA molecule where we see a backbone. This is the thing on the left. This is the backbone where the letters are attached to. And each letter, it is a nucleotide. There are just 4 types of nucleotides, and we see from the top, we see an A, then we see a C, then we see a T, and then we see a G. These are just abbreviations for the 4 kinds of nucleotides. And so these nucleotides are attached to the backbone, okay? And so actually also this strand is really directed in the sense that there is really a beginning and an end, because the ends are marked. You see the 5' end, this is what we would call the beginning of the string as computer scientists, and the 3' end is what we would call the end of the string. And so in general, this is just the string ACTG, but you can have any string of any length, almost imaginable, of letters, and that is a single-stranded DNA string. Now, there are two very basic operations that are possible with DNA. Because DNA, of course, we all know, encodes our genetic material in every cell of a living organism. But in this talk, we will absolutely not work with natural DNA. We will work with synthetic DNA. And so a very important technology that has become available over the past 20, 30 years and is now really commonplace is that of DNA synthesis, by which we can synthesize any desired string. So basically you have machines which are DNA synthesis machines, and basically they have a terminal or whatever. You just type in, let's say, you type in a string, A, C, C, G, T, C, A, G, and out comes a test tube with, in solution, many, many copies of this strand of the string that you entered. So this is possible up to length 100, but using manipulation operations that we will see later, you can actually concatenate strings. So if you want a longer string, you just make the parts and then you concatenate them. So that is something that's very important, so we can make synthetic DNA. And that will be, in DNA computing, that will be the data carrier. That will be the carrier where we will store our data. We will store them as these strings. And the reverse operation is also possible and has also become really commonplace over the past 20 years. And that is that of sequencing. That's another machine where you pour in the test tube with the DNA molecules, and out comes the string, the sequence, which we can then process using computer science methods. And so you can go from a string, digital string, to an actual DNA molecule, and you can go to the reverse. So that these two technologies have really enabled a completely new way of thinking about working with information, yeah? Where we store information as molecules. Now, why would you want to do that? Well, there are several intriguing reasons why it is interesting to at least contemplate or think about using DNA as your data carrier, as opposed to, well, if we think about computation, normally in theoretical computer science, we think of computation on a Turing machine. And there the data carrier is one long string, basically. It's the tape of the Turing machine. So one long string. Or if we think about computer science, computing model where we use a random access machine, for example, a classical abstraction of a normal computer, there we think of our data as stored in a long array of numbers, a huge array of integers, which is our random access memory. But now, so in DNA computing, the idea is going to say that our information is going to be carried by a set of DNA strands. Yeah? Think of a test tube with, in solution, many copies of many different strands, of different strings. That is now going to be our data carrier. And let's see what we can do with it. That's the idea. Now, why is this interesting? Because actually, there are a number of reasons. The first is the capacity. The capacity is enormous, because we are working here on the nanoscale, which is like the smallest imaginable scale that we can imagine, actually. Yeah? That you have a huge capacity. If I would just take the theoretical capacity, I would just say that, okay, I have a string. I have a very long string. Let's say a string of 450 exabytes. An exabyte is 1,000 petabytes. Petabyte is 1,000 terabytes. Terabyte is 1,000 gigabytes. So let's consider a string of 450 exabytes. And let's just theoretically think of how heavy would be the DNA string. Or let's say maybe if you cut it in pieces, the parts together, how much would they weigh together? They would just weigh 1 gram. Yeah? So that is unimaginable, basically. But of course, that is just a theoretical thing, because you would have just a single copy of your data, which is not enough. I mean, if you want to work with molecules, you always have to need your molecule species in an abundant multiplicity, so that you will not miss things. Because, of course, when you work with molecules, things are never binary or digital or exact. Things will always go wrong, and some things will fail, some things will succeed. So if you really if you really take into account everything that you need to make this completely reliable, like you use duplication, you use encoding to avoid errors, etc., then you still get a good capacity of 2 petabytes per gram, yeah, with very reliable encoding and decoding. And there was a very interesting experiment reported last year where they took a home directory of someone with many files, some videos, some photos, some Word files, some PDF files, some Excel files. They encoded it completely in DNA. It was just a test tube of DNA. Then that DNA was freeze-dried. How to say that in English, I don't know. So what they remove basically the water, but the DNA is intact. And then they just have something that is extremely robust. They just have a capsule with dry DNA, and you can do anything with it. You can drop it on the floor, you can put it in a deep freezer, you can do anything with it. So what they did, they put it in a DHL envelope, and they sent it around the world. They sent it first to Japan, and then in Japan it was sent back to San Francisco. And then another team completely decoded the DNA using DNA sequencing. And they were able to completely reconstitute this directory. So the videos, the Excel files, the PDF files, they were all there. So that's quite fascinating. So let's say for data archiving, I would even dare to say that DNA is probably the technology of the future, or something similar, yeah, will probably be a technology of the future. It might not be DNA, it might be maybe other molecular material, but such things are going to be the future, at least for archiving. Yeah. Good, but now I'm not an archive scientist. I'm a database, like Hendrik said. I'm a database researcher, and so we are interested in databases. So when you hear about these possibilities, this potential of DNA as some kind of very robust, very high capacity, and very indestructible technology. I mean, literally. I mean, if I drop a hard disk, or if I take a solid state memory and I take a hammer and I hammer it, it's gone, right? It's destroyed. But if you take some dry DNA in a plastic flask and you hammer it, there's nothing wrong. Yeah? So I mean, this is extremely indestructible. It is miniature. It is a completely different carrier. So it is fascinating to think, what could we do with it? Yeah. And from the perspective of databases. Now, a database is very different from just an archive, which you can encode, store, and then later, when you need it, decode. And maybe the decoding will take a lot of time, etc. With a database, you want really a system where you can structure your data, restructure your data, have constant access to it. You can query the data, ask complex queries, get the results. Yeah? So for that, you need much more than just archiving. You need a good data model. So how are we going to model data? Like in classical databases, we use the relational model, where a database is just a bunch of relations, where a relation is a set of tuples. That's a very nice model. We know how to work with it, and we have good query languages based on the relational algebra, which are just operations on these relations that allow us to derive new relations and do everything we want. So what would be the equivalent of the relational model if we would use a completely different way of representing information as a test tube with DNA molecules? Okay, so that is the question that I want to address. And so the outline is that I will first talk about the most important operation on DNA, that is the operation of hybridization. And then I want to introduce to you DNA computing. So what are typical things that you can do with DNA from the perspective of computing? These are operations from biotechnology, yeah, but that you're now going to use to perform, let's say, computations, or at least data transformations, yeah, as we are used to in databases. And I will introduce you to DNA computing by taking the relational model as some kind of inspiration. And we will see that it's very easy to represent a database relations in DNA. And then we will just, as a proof of concept, think about how could we perform the operations of the relational algebra, which is a basic set of operations on relations. It is 5 or 6 operations: union, different, Cartesian product, selection, and projection. Yeah? And we want to see how could we achieve these operations in DNA. And that will give us some inspiration of how an actual good DNA query language would look like. And we will carefully, while doing this, we will see which operations we need to achieve this. And then, so the set of operations we need on DNA to achieve the relational algebra will give us some kind of good basis to then design a new query language. And we will see that this new query language is actually very different from the relational algebra. It's not like we just create a clone of the relational algebra. This will turn out to be something completely different, appropriate for the DNA model. Yeah? And we will call this language DNAQL. This will be a programming language that can be used to write. You can write programs, you run it. It will be run by some, let's say, some automatic lab robot. It will execute the DNA manipulations. Yeah? And this query language has some nice properties which we will see. It has a type checker because things go very wrong in DNA. So you need, why do you need type checking in programming languages? Because you don't want your programs to go wrong while running. You want the compiler, the type checker, to already find the errors before. In DNA computing, this is even more important. And we will also look then at what can we do with this query language. What is its expressive power? Okay. So the most important operation on DNA, a natural operation on DNA, is hybridization, or also called base pairing. Because these 4 types of nucleotides that I introduced, A, C, T, and G, they have a very natural complementarity relation. Namely, A and T are complementary, and C and G are complementary. And when complementary bases are close together, they will naturally form a bond. This is called base pairing. Now I can show again the same picture from before, but now we look at both sides. And indeed, you see that the G and the C, they are bonded. You see these dotted lines here, yeah? And you see that the T and the A are bonded, and similarly, yeah? Okay? So you see that the complementary base pairs are now bonded. And so effectively what we have here, if we have a string, ACTG on the left, and we have the complementary string in a sense, because it runs. The interesting thing about this base pairing is that if you have a sequence of complementary bases, and that actually the bonding happens in the other direction. So if I have a T and a G here, then I should have a C and an A in this direction. So you see that the 5' end is now here. Okay? This is how it works. I did not invent this. This is how DNA works. Okay? And so we can mathematically very easily formalize this by introducing the complement of a string. So the operation of complementing a string is very easy. You reverse a string, and then you complement every base pair. And that will be another string that will attach completely to the string, to the original string, by base pairing. And the longer these strings, the more robust this base pairing is. So here is an example. This is the example from the previous slide. We had ACTG, we reverse it, we get GTCA, and then we complement everyone, so we get CAGT. And here is a longer example. Okay. Now, the fundamental operation of hybridization is when 2 single strands meet, come close to each other. And these 2 single strands contain substrings that are complementary. Then they will meet and they will hybridize on these 2 substrings into a double-stranded complex. Yeah. So we see here 2 strings. They contain a substring which is complementary, AACTG, and this one, the complementary. And so they will, at this place, in this substring, they will naturally form a bond. Yeah. And this bond is very stable at normal temperatures. Yeah. Now, at normal room temperature, let's say, because this is the essential operation that also happens in our cells. Yeah? hybridization, and it typically works at room temperature. So that means that you can always break this bond, and this is called denaturation. You can undo hybridization by increasing the temperature. So when you increase the temperature, the molecules will shake vigorously and these bonds will break. And when the longer these strings are, where the base pairing is taking place, the more stable this bond is and the more it will take to break it. Okay? And the temperature that you need to break a complementary string depends really on this sequence. Yeah? And it is called the melting temperature of this sequence. Okay? So you see there are some subtle things that you have to take into account. So that is really a very important operation, and it happens for free. We get it for free. Nature does it. We don't have to do anything for it, and we will take advantage of this operation as much as possible. Yeah. Now I want to introduce DNA computing. So what kind of things can we do with DNA to perform data manipulations? And to do that, I will take the relational algebra as a starting point. So let's first agree on some way to represent relations, database relations, so sets of tuples, or if you want, records with attributes, yeah, how to represent this in DNA. This is extremely simple because we have strings. Yeah. Now, first we should agree that just working with a 4-letter alphabet is a bit, is not very pleasant, right? On a digital computer we have the binary alphabet 0 and 1, but the first thing we do is we code. We go one level higher and we use the Unicode alphabet or the ASCII code. Yeah? We use something more flexible. That's also what we're going to do here. So we're going to introduce an alphabet of what I call value bits. Think of the Unicode alphabet or think of the ASCII code. Yeah? And so we're effectively, just like an ASCII letter represents a string of 8 bits, also here every value bit will represent already a string of A, C, T's and G's. And so that allows us to use a larger alphabet that's much more flexible. So the idea is that each letter of the value bit alphabet is encoded by a DNA strand, and it is very important that this is an art in itself, and I could give a talk about this topic on its own. It is a very difficult topic in DNA in general, not just DNA computing. And this is to design a nice set of code words that can represent our larger alphabet. Because it would be a disaster, for example, if I have 2 letters that are coded by DNA strands that are, for example, complementary. Because 2 letters would suddenly stick together for no reason. Yeah? So we want to represent our alphabet, let's say our ASCII alphabet, by suitable DNA strands that do not interact with each other. And to design such a set of code words is already an art in itself. It's actually an NP-complete problem. Yeah? But okay, we have to live with it. And also these alphabets do not have to be too large. Okay, okay, so that gives us this alphabet lambda that we will use. And so now we agree that any atomic data value that we want to store as an entry in our database relation will be a string of these value bits. Yeah? Just like in normal computers, we store strings of ASCII symbols or strings of Unicode symbols. Okay. And we will need 2 more alphabets. Since we are going to store records with attributes, we're going to use an alphabet omega of attributes, just to represent the attribute names. Yeah? This will also be encoded in DNA. All these alphabets are encoded in DNA. And we will also need some special markers in our DNA. It is not so surprising that we need markers in the DNA strings to indicate special places, for punctuation, to say where does this stop, where does this start, and also to indicate places where, for example, we can cut DNA, as we will see later. And we will actually, in our model, we need 9 such markers, hashtags. So we have hashtags. #1 to #9. Okay, and now it is really simple. Suppose I have a tuple T, yeah, over attributes A to B. I have a set of attributes A, B. They have this tuple has values T of A, T B. then I will just encode it as a long string where I put all the attribute values next to each other in a long DNA string. And I punctuate this string. I indicate where everything starts by always working as follows. I have #2, then I have the attribute, #3 to enter the attribute, then I give the value, t of a, that's the value of the tuple t for attribute a. Then I have #4. And I do that for all the attributes in order, and I get just a long DNA string. That's how we're going to represent one tuple, and now a relation being a set of tuples will just be a set of a test tube, basically, with containing all these strings, all these strands. Typically, every tuple is represented in a large quantity of copies for things to work. Okay. So that's just agreeing on something. This is actually not important for the final DNAQL model that you represent tuples in this way. If you want another way, you can do it in your way. It is not essential, but it is just it's just something we use to show that you can at least do the relational algebra. Yeah? And this will be for us an important characteristic, because the relational algebra in database is like the basic level of computing power you need to manipulate data. So we want that. We want to have that. Okay, now let's do something with this data. Yeah, and the first thing we want to do is an extremely simple operation. Suppose I have a test tube, yeah, with containing a database relation, and I have just one value bit a. I pick a value bit a, and I want to retrieve all tuples from the test tube that use this letter. For example, I store all your names, and I want all the people that have an A in their name. It's that simple. That's the query. If you can do that query, yeah, that's a very basic query. So how does it work? Well, it works in 3 basic steps. We will add the complement of this value bit, yeah, to the test tube. Yeah? We will add it in surplus quantities. And then the idea is that, of course, all the tuples that contain A, they will stick. Yeah? So this complementary short strand will stick to all the tuples that contain an A. And so if we just have a way to retrieve the tuples that have been bound to a sticker, we're fine. Now, how do you do that? How do you retrieve the tuples? Yes? No, this will not happen, because I will encode that this is this. So all the DNA strands that are used to represent the letters, they come from a set of DNA code words, and they do not stick together. Yeah. Yeah. This is very important. This is this code word, this NP-complete problem that I said in the beginning. This is the first step. But I went over a little bit quickly there. So if we can find a way to retrieve the tuples in the solution where a sticker has been bound, then we're fine. And this is possible. The idea is that these stickers are not just thrown in like that, floating freely, but they are kind of immobilized so that we can later manipulate them mechanically. And there are many technologies for this. One technology is to use tiny magnetic beads where all these stickers are attached to. So one bead is a bead, so let's say a sphere, a small sphere, where maybe millions or hundreds of thousands of these stickers are attached to. Another technology is where you attach these stickers to a surface. You attach them as little, I will illustrate this on the next slide, where these little probes, as we call them, these little stickers are attached to some kind of threads that are growing on a surface. Just one, we need some way to immobilize these stickers. And then once a tuple sticks, it is immobilized too. And then if we can insert the probes, hybridize, let it hybridize automatically. And then if we simply flush away the tuples that are not immobilized, those are the ones that have not stuck. Yeah? And then we're left with the ones that have stuck. And then we can retrieve them. That's the idea. So here is a small animation that I made. That is like how it is in a DNA chip, because this operation is so essential that people already have chips for that. So there are already DNA chips. Think of like a normal computer chip. It looks like the same. except that there is no electricity flowing, but there are microfluid flows of DNA floating through this chip. And inside this chip, you can program them with probes that will probe for something to detect. And for example, if we put the probes, the complementary A bar there, and then we let the flow come through, and the tuples that have an A, they stick. Okay? Let me show that again, because it took me a while to program that in PowerPoint. Okay. And so we have the tuples that contain an A. We clean up by basically somehow removing. How this works is not important. We remove the probes and we have it. Okay, so to do this basic operation, we have used already a number of operations on DNA. Yeah? So I will introduce the database query language, or some kind, if you want a programming language, it's a DNA programming language that we call DNAQL to represent what we have already done. What have we done? We have a test tube R, which contains a relation. We have added to it, so we have the union, the set union. We can have a set union, that's a basic operation. It basically means pour two test tubes together. We added an immobilized A complement. So this is called a probe. You can only do it with value bits that are complemented. So these are the probes that you need. We add them, we let it hybridize, we flush, it means remove things that have not stuck. Yeah, and clean up means remove the immobilization, and we are left with. So these are already 1, 2, 3, 4, 5 operations of DNAQL. And we use them in this order to do the selection, but you can use them in any order. Yeah? Because DNAQL is a functional programming language where you can apply your functions in any order you want. Okay, good. Now another very important operation in the relational algebra. This is already much more complicated to do, is the Cartesian product, but it is essential that you can do that. I mean, if you're limited to just very simple queries where you just say, give me all the records that satisfy a simple property that can be decided on each record separately, all you need is some kind of selections. But in database query processing, we do things like joins. We relate tuples from different tuples together, and based on their relationships, we will do things. So we want to compute joins. And so the underlying mechanism is to be able to combine pairs of tuples. I have two relations R and S, and I want to take their Cartesian product, which means that I take all the pairs of tuples where T1 comes from R and T2 comes from S. And I want all the combinations. Once I have done this Cartesian product, I can now work with that relation and continue to work with that relation to express, compute a more complicated query. So that's an essential basic operation we want to do. And it turns out that this is already quite challenging to do with DNA. Yeah? I will explain this also, but a little bit more quickly. So the idea is that since every tuple begins with #2 and ends with #4, what we could do, if we could use a sticker, but now not of length 1, but of length 2, which is the #4 complement and the #2 complement. That means that this will stick to the end of T1, this will stick to the beginning of T2, and we have effectively concatenated them. There is one problem, however, is that this sticker will just hold these tuples together temporarily until we denaturate, and then the sticker will come loose again and they will drift apart again. So we want to concatenate them permanently. Now for that, we need an extra operation. And in biotechnology, people use enzymes for this. Enzymes are special proteins that facilitate certain chemical reactions. And this enzyme will do the following. It will see that there is a backbone that is interrupted, and it will fix the backbone. It will really make the bond here on the backbone, and that is now permanent. Because let's say the horizontal bondings are much stronger than the vertical bondings. The vertical bondings, as I showed you, by increasing the temperature, they can come loose. But these horizontal bonds, they keep until, let's say, 90 degrees, 100 degrees, maybe even more. Yeah? Okay. it's actually quite striking how robust that DNA is. I mean, really, you cannot destroy it. I mean, for example, there are laboratory protocols to extract DNA from something. Yeah, extract DNA from blood or from other tissues or samples. And basically, these protocols, I've done them. I've followed a lab course in biotechnology, and we did that. And basically, the protocol consists of doing lots of destructive things to your sample. Turning it very rapidly around, adding poisons, lots of things, until only one thing remains, and that's the DNA. All the rest is already destroyed. Yeah? So DNA is incredibly robust. Anyway, so once this ligase has done this ligation, you have a solid concatenation. Yeah? So we could say, oh, it's very simple. Yeah, we just add this sticker that will keep the ends of the end of the first tuple and the beginning of the second tuple together, and then we let it hybridize. We apply ligase, and we're finished. But it's not so simple, because note that each concatenation still has this property of beginning with a 2 and ending with a 4. So nothing keeps the hybridization from continuing. So we get some kind of chain reaction, which we don't want. We don't want an uncontrolled chain reaction, right? So what will happen is that I have 2, they will concatenate, but I have many of these stickers. So another sticker could now attach here, and some other strand will again be concatenated, etc. Yeah? So that's what we don't want. So we don't want this chain reaction. So there is a solution that is a bit technical, but it allows us to introduce some more operations of the DNAQL language. Yeah? But I have to speed up a little bit, so I will not give the details now, but you can read it in the paper. So if you Google for the title, you will find a paper of this talk. Yeah. So the idea is basically that we're going to not use 4 and 2 to attach the tuples, because that leads to a chain reaction. We need some other hashtags. Yeah? So we first add 5 here, 1 to the beginning, and we use that to concatenate. Yeah? The only problem then is that we have now concatenate them with the different hashtags, but now we want to get these things out again. We want to get them out because they are not in our normal encoding. And to do that, it is a complicated procedure where we introduce a new operation. Yeah? The first step is blocking, but I will not say something about this. This is basically an operation that you can do to avoid hybridization in other places. A second step is bind to a probe. The third step is add the sticker that we really want, because we have concatenated them there, but we want to concatenate them here. Yeah? And then the most important one is adding an enzyme. That's another enzyme. This is called a splitting enzyme. Yeah? And these splitting or restriction enzymes, they will split DNA in certain locations. Yeah? And there are many restriction enzymes on the market, let's say, found in nature. Yeah? Nobody can make a synthetic restriction enzyme. Actually, this is all still very unclear to us. But the point is that, okay, we need just a very small repertoire of splitting sites to recognize. Yeah? So the idea would be that we use our code word design in such a way that these restriction enzymes will work there. And this is very important, splitting. So you split at a certain hashtag, and then the tuple will come loose. So the idea is basically you create a circle of DNA. You could create circular DNA so that you can cut it so that it still remains one whole. It remains whole, but you have cut it in another place so that you get the configuration you want. But this is a bit complicated. I will now quickly go over it. There are other operations. The projection operation in the relational algebra is to throw away some attributes and only keep some of the attributes that you're interested in. This is done by similar methods. Renaming is also done by similar methods. And there is one operation that is very powerful in the relational algebra. It is called the set difference. It's very simple. You want all the tuples in one relation that do not appear in the other relation. It is really a set difference. And this is the most tricky operations to do in DNA. There is a technique called subtractive hybridization that is used. It is used by biotechnologists. It is routine, but it is very sensitive. And it is the most error prone. That's actually very interesting because also in the relational algebra, the set difference is the most powerful operation. I mean, if you take the relational algebra without set difference, you get a very tractable language that you can understand very well. If you add the set difference, you suddenly get a very powerful language. And it's interesting that in DNA, apparently something similar happens. Okay, we have seen now the DNA, we have seen already a lot of DNAQL operations. We have test tube variables, we have probes and two-length stickers, that's all we need. We don't need longer complementary strands. Our model uses just probes and two-length stickers, that's all. Yeah? Then we have union and set difference, and then we have hybridize, ligate, flush, cleanup, split, block, and block from. This blocking is something I stepped over, but it is to avoid hybridization in certain places. So you would think, okay, how much more is he going to introduce? But no, the good news is that it's almost finished. DNAQL is finished by basically adding two more operations. We have a block except, that I will not talk about, and a for loop. Yeah? Now, the for loop is very interesting, so I want to talk about this. Suppose we have already seen a very simple selection. I have a relation, and I want all the tuples that use a certain letter. Yeah? That's very simple, right? I want to do something more. That's similar to all the names of you that contain an A. That's not very interesting. Suppose I do something else. I say I want okay, it is hypothetical, but just as an example, I want all the people whose first name is equal to their family name. Like, there are actually people, Lang Lang, for example. He's a famous pianist. Yeah? So there are people, first name equal to second name. So in general, this is some operation you would do after a Cartesian product. And then this allows you to do a natural join or an equality join. Yeah? You first take a Cartesian product, and then you want this attribute should be equal to this attribute. How do we do that? So A should be equal to B. Yeah? Now, the idea is very simple, actually. We're going to introduce a for loop that allows us to iterate, yeah, over the length of our strings of elements. So remember that every attribute value is a string of value bits, and we add a for loop that allows us to iterate over the positions of these strings. So, and then we get something, a DNAQL program that looks like this. Yeah. This is a syntax we invented for it. You may or may not like it, but we say, so we take R. We take the idea is the following. Yeah. So we take S. Yeah. We initialize it with R. Yeah. And then we're going to iterate over all the positions of our strings. Yeah. And we're going to say, we're going to filter all the ones that have the first, so I goes from 1 to D, let's say, where D is the length of the strings. D is comparable to the word length of a digital computer. Yeah? In a digital computer, the word lengths are like 64 bits, so the dimension would be 64. And we need some for loop to iterate from 1 to 64. Yeah? We don't want to hard code this, so this is a feature of our language. It works on any word length that you install. So the same program works uniformly over any word length that you want. Otherwise, it would be really cheating. Yeah? Anyway, so we select the first bit should be 0, and the first bit of B should also be 0, or they should both be 1. And then you add that, and you continue with the second bit, etc. So our language is this one. This is the syntax. We have a programming language. It is just a programming language like any other programming language, basically, except that its semantics is completely defined in terms of DNA complexes. Yeah? And so now I have to say very quickly, because I'm running out of time, say something very quickly about how the semantics of this query language is really defined, because it's not defined on relations. I just used relations to illustrate this query language, but the real semantics is based on a data model that we have introduced, and basically we have observed all the structures that come up while trying to express the relational algebra, and we saw that we need just this kind of structures, and that seems to be enough to do relational algebra. And our idea was, what if we just focus on these structures and then do anything with them? Not relational algebra, but anything you want, any DNAQL program you want to write. Yeah? And this is the model of DNA complexes. Yeah? And so, as I said, during the execution of a DNAQL program, even if you start with just a set of tuples, you will form more complicated structures where bonding takes place, immobilization takes place, etc. Yeah? And so we formalize these complex structures by directed graphs, and this will be our data model. Here is an example. Yeah? Suppose I have the blue. The blue are the strands. So I have 4 strands, but they have been, you see the strands have been joined together by stickers, which are the green things. Yeah? Some piece here appears to be blocked. That's the black thing. Remember, we have blocking. We also have an immobilized probe. So these are the features of our model. And so now complexes are any structure that can be formed using these data constructs. And we just abstract this as a directed graph structure so that you can think about it mathematically and formalize it mathematically. So we have completely formalized the DNAQL language as a programming language for manipulating, transforming graphs, directed graph structures, but not any graphs. They have to be graphs of this kind, okay? So you see, every position is represented, every base basically is represented by a node, and base pairing is introduced by some special edges, and nodes are marked whether they are immobilized or not, or whether they are stickers or not, whether they are blocked or not. And that's it. So we have a directed graph model, and this is our data model. Okay, okay, now the last thing I want to briefly say something about it is that we also need a notion of data types. Yeah? Our data are these directed graphs, but what are our data types? Well, our approach will be that the data values, yeah, which are strings of value bits, this is the data. So you have a big complex, but there will be strings of value bits in places. And this is our data. And all the other DNA strands, they are just there for manipulation and structuring. Yeah. So the type of a complex is simply the complex where you replace, yeah, all the strings of value bits by an asterisk. Yeah. So for example, type of this relation, which contains 5 tuples, is just this. Just an example. It says it gives you the structuring, but it omits now the actual data contents. And very important is that also now the actual length of the value strings is gone. So we have a uniform data model that works for any length that you want to set up. Yeah? So our model is not restricted to a fixed length encoding. Okay, and then you can do things like type checking, which we have tried to achieve. Yeah. So because how much time do I have? 5 minutes? 2 minutes? Okay. Because some of the operations that I have introduced, they have important preconditions in order to work in the lab, to work in chemistry. Some operations do not have such preconditions. The union, for example, has no preconditions because I can always pour 2 test tubes together. There is no precondition for this to work. It will always work. Yeah. But other operations have some preconditions. Think about hybridization, for example. Yeah. Remember that we wanted to avoid this chain reaction. So we should be able to determine just on the type of the complex where we're going to apply hybridization, just on the basis of this type, we should be able to decide whether it will run off in a chain reaction or not. Yeah? And we have devised a polynomial time test that can actually check whether this happens or not. Okay, that's one example of type checking. And so using this kind of type checking, we can, given an input, and I will immediately give the example, given an input type and an operation, we can automatically derive the output type so that we always know what kind of structures we're working with. For example, if we have this little program here, it is an expression E. It is a sub-expression of a program that involves one variable x to which we add a probe A and we let it hybridize. So, but if we know that x contains complexes of this simple form, then we know that the probe can either it can stick or it cannot stick because they are not complementary. There are two possibilities. But so all the possible results are present. Yeah? So some probes will be left, some unmatched will be left, and some matched will be left. And so if this is the input type, then this is the output type. And so we have devised also a complete semantics of our language on the basis of types. Not on the real data, but on types, so that you can run your program before running it on actual DNA data. You can already run it on the type level and understand what's going to happen before actually doing it in the lab, which I think is very important. Okay. Some operations are really difficult to type check. You even have to solve some, well, difficult. You have to solve some linear inequalities over the integers to actually do that. It has to do with lengths of DNA strings, etc. I will not go into details. And so we have a type inference algorithm that has all the nice properties that you want. Yeah? Soundness, maximality, tightness. And to conclude, I want to say one last thing, is that this model allows us to understand what we can do with DNA computing for databases and also what we cannot do. Yeah? Because we have a result that I like the best actually of our results, and this is the following. We have tried to do the relational algebra, and while doing this we gained understanding of what kind of operations on DNA you need. We have collected these operations and made a completely independent programming language from it that looks very different from the relational algebra and has a data model that is very different from relations. But now the nice thing is that, what I really like, is that we can prove actually that any program in this language can actually be simulated in the relational algebra. So you get, in a sense, the right level of expressiveness. You get nothing more. It is not like we have said, to do this operation we need this, and we need this, and we need this. Now we put them together and maybe we get a much more powerful language by combining the operations in another way. We get something that is much more powerful in the relational algebra, but probably by designing it in the right way, we ended up with a nice language that is completely orthogonal. It has no artificial restrictions, but it can be simulated by the relational algebra. So that's our second theorem. So every well-typed DNAQL program for given input types can actually be simulated in the relational algebra. And for those of you who are not database people, you should know that the relational algebra is really the basic level of expressiveness that you want for a basic query language. Okay, so this is an example of how it works, but I will conclude now. So this is what we have done. I've said it a number of times. We made a language by taking a minimal set of DNA computing operations needed to simulate the relational algebra, but then made a data model and a programming language that completely stands on itself. And it is very satisfying to find that it's actually, in the end, equivalent with relational algebra. Now, all this has been done purely on the theoretical level. Yeah? So what we have done basically is we have learned a lot about DNA computing. We have read papers experimental papers, yeah, that explain this technique, this technique, this technique. So we knew which techniques are feasible in the lab. And using this knowledge of these techniques, but just theoretical knowledge, we made a theoretical model. Yeah? Of course, what should be really done now is to experimentally validate this language and understand which things are complicated, which things are easy. It would be really nice if there would be some kind of correlation between how difficult something is to program in the programming language and how difficult it is really to do in the lab. That would be nice. For example, the Cartesian product is a basic operation in the relational algebra, but in DNA it's very complicated to program. Yeah? So that would be very interesting. Something else that I'm very interested in and that I'm working on right now is to understand the reliability of this model. Because things can go wrong, hybridizations might fail, restrictions might fail, things might just go in the wrong order, and reactions might not be ideal. Now we have given a completely ideal semantics in terms of these graph structures, which is mathematically completely precise, but in reality you need something much more error-prone and to understand the reliability of your errors. Okay, so I think I will stop here. I hope I've given some idea of what we have been doing. Thank you for your attention.
Just a quick question, what are your access times on this database?
Yeah, that's indeed the question that many people ask. So for the moment, all this is very slow. Yeah? So it is like, let's say, hours, or maybe even a day, yeah, to do these operations. Yeah? Like, for example, letting hybridization take place, yeah, you have to let it incubate, let's say, for 15 minutes. Yeah, if you want to do this kind of separation, affinity separation based on probes, okay, it is a complicated. These are complicated operations. So this is all still very new, and this is all very slow. So it is absolutely not practical. Yeah? It is practical already now for very specialized operations that have been really, let's say, hard-coded, or special machinery by these DNA chips have been made. But of course, let's say the general data manipulation capabilities of DNA computing, they are very slow. And people, exactly to deal with this, this is where I put a pointer here, to deal with this problem, it would be much nicer if you could do DNA computing in an autonomous way. It might still take a long time, but at least it will brew by itself. So the ideal would be that you just put all the ingredients, also the active substances that will do the operations, together in one pot. This is called one-pot computing. Put them all in one pot and just let it brew. And it will self-assemble, and there is a very nice theory of self-assembly, how crystals grow or how tiles assemble to some pattern that you want, to perform some computation that you want. And people are really actively looking now in DNA computing for mechanisms that could achieve this. So there's still a lot to do. I mean, this is still a very young and active topic where there is still a lot to explore.
It's a related question. So you don't right now have the cookpot thing working yet. So you have to sort of do multiple steps. In between, the lab robot will have to do some other stuff and then let it brew again, right?
Yeah. Yeah.
So how many of those sorts of steps on average for your average operation?
Well, yes, that's
quite nice. So if you write a program in DNAQL, you use its primitive operations, and each primitive operation is indeed something that that is kind of more or less the same complexity of actually doing them in the lab. So it's not. We have tried to not add one operation that takes a day and another operation that takes 5 minutes. Yeah, except maybe for this subtractive hybridization, which is a bit tricky.
Be forced to change your language when a new chemical technique is invented to.
Yeah, that's a very good point. Yeah.
Okay.
That's a very good point. For example, there's now a new chemical technique that is related to this. Actually, most of the yeah, but that's a good point in general. Yeah. No, I completely agree.
Okay.
Question about how the operations modify your source material. You start out with some molecules that have been synthesized, and then you apply operations on that, right? But that also modifies the original material, so when you selected the all the names that contain an A, then, I mean, you
Yeah,
lose
it's not
those
all.
from the solution.
Yeah.
And for example, if I wanted to find somebody in the telephone book, I
Yeah.
synthesize the telephone book and then I select them and I get the telephone number. But
Yes.
if I then want to find somebody else, I have to kind of synthesize the telephone book again.
No, yeah, you don't have to do
How,
that.
how bad
Yeah.
is that?
Yeah, that's a very good question. So the operation of DNA,
In a sense, they are not destructive because we have a functional language, which variables, and you take a variable as input, but the result will be put in another variable, well, in a sense, or will be fed as a result of another operation. But the idea is that how can you preserve the values of the variables to begin with? Yeah? And this is actually not really a big issue because typically the assumption is that every molecular species is present in an abundant size, abundant number of multiplicity. And also, so you can always take just half of your test tube, for example, or take a piece of your test tube. It will still be representative for what it contains. And second, it is also very well known and very basic to multiply a set of DNA strings so that you get, you boost it up again so that you get again many copies. Yeah? So suppose I have a test tube which contains a million different species of DNA, yeah, but each species is present also a million times. Yeah, I take half of it, so I only have 500,000 copies of each species, which is maybe not so good. Maybe I do it again. I have only 100,000, maybe after a few times. Then I can boost it again, so that I get again a million copies of each species, and this is a well-known technique to do that. So you can preserve your species, basically. Everything is error prone, and yeah, it should be understood how to control this, if at all possible. Actually, I think the future of DNA computing, but now I'm talking just in general, the future of DNA computing will probably never be for general purpose computing. Yeah, it will probably be, and it is also envisaged in this way, for a very special purpose, like smart things, like smart drugs. It's a bit scary, actually. So you inject a small DNA computer that does something very specific, like recognize a specific pattern or temporal pattern, and then release something, for example. Yeah? These kind of things. That is already feasible now, but I think it will always remain restricted to probably pretty special purpose things, never like general purpose computing. But still, I think it's our duty to at least investigate in principle what is possible. Yeah. That's what we have been doing.
yes. So that's
Basically, our first theorem is that we can complete this in the sense that we can simulate a relational algebra. Yeah. Well, no. This is not known to be complete. It is known not to be complete. I mean, the relational algebra is not complete, but it gives a very well understood level of expressiveness. Yeah? Like the relational division is expressible in the relational algebra, so you have it. Yeah, and so this is a basic set of operations that gives you a level of computability that is equivalent to what you can in logic. Any operation that you can explicitly define with a formula in first order logic, this is what you get basically. And this is a very natural level of expressiveness that is well known from the theory of database query languages.
That it would probably be easy to add transitive closure to what you're doing, so being more powerful by relational algebra than relational algebra. By not doing this 500, simply let them all stick together.
yes.
A very good question is what if you allow recursive hybridization, what exactly do you get? Yeah, it is a good question, but of course you will also. I mean, the problem is that, well, in this work we have tried to do the relational algebra, and then we always need to be really sure of what the next result will be to apply the next operation and the next operation. So there we did not. We tried to avoid it. It was considered for us something that you want to avoid, but of course, in this one pot thing that I talked about, the autonomous brewing kettle that does the computation, there you actually want such recursive hybridization. And actually, all the techniques known for simulating such self-assembly growing systems, they are based on hybridization that keeps on going. So it is a very relevant question, but there remains a lot to be explored.